Okay, so I'm going to get started. Today's announcements, I updated the Chapter 14 sapling due date since we finished the chapter on Monday. So now it's due Monday next week, 9 a.m. I usually have it set 9 a.m. just so it's done right before lecture starts so no one's frantically working on it during lecture. And then Chapter 15 is now open, and I've tentatively set the due date for that like the Monday 1 week afterwards. After Chapter 14 is due. That may be updated depending on how we go. And then the Chapter 15 notes are posted now too. And then we have a quiz today and tomorrow in recitation. Everything up through Friday last week is fair game. Okay, questions about any of that? Okay, cool. All right, so the notes that I posted, I ended up deciding to switch around the order of topics a little bit from how I covered it on Monday. So I actually moved cumulated dienes so they're before conjugated dienes, just because conjugated makes more sense leading into the next reaction that we're about to do. But all the actual contents that I covered is still the same as it is in the notes. I just jumped around a bit from how I published it. Okay, so last time we looked at a little bit conjugated dienes where the idea is that however you draw it, you've got this chain of carbons where every carbon is involved in a double bond. So basically, you've got this continuous chain of sp2 hybridized carbons. If you had an sp3 hybridized carbon in the middle of that chain, then that would break the conjugation, and then they'd be isolated dienes. Okay, so we're going to spend a good part of this chapter looking at reactions that conjugated dienes can do just because they happen to be conjugated. So this is going to be different chemistry, or somewhat different at least, from things that regular alkenes can do. Okay, so the first and probably the most useful reaction in this category the first one in this category that we're going to cover is the Diels-Alder reaction. Which sometimes gets abbreviated as DA, Diels-Alder. Okay, so I know I harp on this a lot, but this is a way of making carbon-carbon bonds in a very specific way, so it's also going to be very useful for doing syntheses. So the general idea is put together a 4-carbon bit plus a 2-carbon bit, and we're going to combine those to make a 6-carbon ring. So we start out with 2 separate pieces and we bring them together and make a cyclohexane or cyclohexene, depending on the exact conditions. Or I guess it's got to be cyclohexene, but it might have multiple alkenes potentially. But we're making a 6-membered ring out of it. Okay, so how this looks is we're going to have these 2 bits. So we need 1/2 is called the diene, and the other half, I'm going to leave this kind of vague for now, because it turns out having the right R groups on there is crucial to get this to actually work reasonably. But this is called a dienophile in the context of this reaction. Okay, so we've seen kind of this phrasing before, like electrophile or nucleophile. This just means something that likes dienes or reacts with dienes. Okay, so the arrow pushing for this is a concerted 1-step reaction. But basically think of it as everything kind of clicks around the circle at once. So you're going to have an arrow coming out of each pi bond. And if you want, you can actually show like to make it easier for yourself to keep track, you can show these little dotted lines for the incipient bonds that are about to close down the ring. So every pi bond is going to have an arrow going one step clockwise or counterclockwise around the ring. You can actually show it either direction, like clockwise or counterclockwise, so long as all the arrows are going the same way. So to stay with the notes, I'm going to go counterclockwise on this one. This pi bond kicks into here. This pi bond kicks into here, and this pi bond kicks into here. So everything just kind of hops one step around the ring, at least all the electrons from the pi bonds do. Okay, so where that gets us is we now have a 6-membered ring, because Diels-Alder always makes 6-membered rings. All 3 of my pi bonds are no longer where they were before, so I've taken the electrons out of this pi bond and made a new sigma bond. So this dotted line became a true bond once I put electrons into it. This pi bond here, its electrons don't need to go make a sigma bond because there's already one here. What they're going to do instead is make a new pi bond right there. And then these pi electrons hop over, make a new sigma bond, so that closes down the bottom part of the ring here. And then I still got the R groups on too. Okay, so the actual mechanism is surprisingly simple as long as you're keeping track of, you have to have arrows coming out of the pi bonds, but there turn out to be kind of a number of details that we need to get right for this to work. So questions about this one first. Okay, cool. So one other kind of variation on this. Dienophile doesn't have to be an alkene necessarily. You can also do a triple bond, like an alkyne dienophile. So this, again, depending on exactly what R is, will work as a dienophile as well. And again, you can sort of make things a little bit easier for yourself if you show like a little dotted line for where the bond's about to form. And again, you can just show the arrows clicking around the circle and making a 6-membered ring. And again, out of the 3 pi bonds you break, 2 of them go to making new sigma bonds to form the ring. One of them makes a new pi bond there on the left, but we still have one of the unused pi bonds out of the alkyne over here in this case. So in this one, you'd be making a cyclohexadiene with its R group still on there. Okay, another name for the product, since we're doing an addition of 2 things, and technically any addition reaction you do this with, you could call the product an adduct because you're doing an addition, but for some reason the term gets used a lot more frequently specifically for Diels-Alder. So adduct is how you could describe this product, and the same thing over here. Okay, so this is actually, I think, the only example we're going to see during this semester of what's called a pericyclic reaction. Which basically just means there's a concerted flow of electrons around a ring or something that temporarily resembles a ring. Turns out there's a ton of other reactions in this category that the book doesn't get into until like, I think 28 or 29, and we don't actually get that far during the semester. But there's actually a ton of really useful things you can do with these just because you're making new rings for a lot of them. But there's also a lot more detail that we're not really going to get into in terms of like orbital phase matching and like overlap geometry and stuff like that. But Diels-Alder is definitely the most useful because it gets us a new carbon ring out of it. Okay, questions about that one? Okay, cool. So let's get into the details on this. First of all, let's look at what R can be. Okay, So this is the first time we're going to see this descriptor, but R has to be an electron withdrawing group, which we're going to start describing as EWG for short. That's actually going to come up a lot in the next chapter too. We're going to see a whole bunch of electron withdrawing groups there as well. But kind of the gist is usually it's going to be a carbon with multiple bonds to something more electronegative. So pretty much anything with a carbonyl, like right at the point of attachment to the rest of the molecule, is going to work great. So like aldehydes, ketones, any kind of carboxylic acid derivative, carboxylic acid itself, could do an anhydride. Like I had this whole list in the notes, but really you don't need to memorize like individual groups. Just look for a carbon with multiple bonds to an oxygen or multiple bonds to a nitrogen. They all pretty much follow the same pattern. Okay. So this is for the R group on the dienophile. And I guess I showed it as two separate R groups on there. Really, you just need at least one per dienophile. So, in other words, this is going to be a pretty decent dienophile, even though it's only got one of the electron withdrawing groups on there. The other one can be an H, and that'll still go okay. Okay, so I'm drawing this dienophile. I'm going to draw a more complicated diene now because things can get really complicated if you're, or at least complicated looking, if you're making a new six-membered ring on something that already has rings in it. All right, so here's a diene. What if we do a diene that's already in a six-membered ring of its own? Numbering is super useful here. So let's say we're going to call this 1, 2, 3, 4, 5, 6, because those are the 6 atoms that are involved in actually closing down the new ring for the Diels-Alder product, or Diels-Alder adduct. But then we also have these 2 other carbons that are sort of in the way and not actually directly involved in the reaction. Let's call them 7, 8. Best way to figure this out is, again, draw your dotted lines in, connecting the parts that are going to actually connect to each other. Because even though these carbons are in the way, they're not actually doing anything for the reaction. Okay, so when we do this, we're going to get a new 6-membered ring, and it's going to have the same numbering that it did over there. So 1, 2, 3, 4, 5, 6. So that's my newly formed Diels-Alder ring. But then I also have 7 and 8 that are bridging the connection between 6 and 3 still. So this might be easier to show like in a 3-dimensional model, but think of it like this whole 7, 8 part like folds up out of the way so that the dienophile can sort of slide in and like click onto the rest of the molecule. So you're ending up with these bicyclic structures that we looked at a little bit in OChem 1, but not very much. And then, of course, you can flesh in the details. We know we need a double bond 4 to 5, and we still have our carbonyl thing coming off of 1. Okay, so I guess key idea here is keep track of what you're connecting to what. We know we're making a bond 1 to 6 and another bond 2 to 3. And so as long as you keep that in mind, you should be able to figure it out. The one reaction that we actually have you guys do during lab for Diels-Alder, which I want to say is next week, it's an even more complicated looking thing, but as long as you sort of figure out where the bonds are going to form, you can keep track of it just fine. So, and the reason we picked something that complicated looking is it turns out it's actually fairly easy to crystallize. Like the old version of this lab we did, it was easier to draw, but just took forever to purify. So doing it this way is a little bit better. Okay, yeah.
Does it matter that the oxygen isn't directly connected to one of the carbons involved in the ring?
Well, so I guess the new ring is this 1, 2, 3, 4, 5, 6. So it is still connected onto 1, which is in the newly formed ring. But yeah, the oxygen itself, like, I guess, so this is just going to be your electron withdrawing group. And in this particular case, it happened to be a ketone, but it could just as easily be in like any electron withdrawing group and it would still do the same job for it. So yeah, yeah. So there's a lot of flexibility there. Okay, so questions about that one? Yeah.
Are there like any other reagents or like solvents that you need to use?
Pretty much no. Like there are some that will catalyze it and make it a little bit easier, but generally all you need to write on the arrow is heat. You guys are familiar with this notation, right? Like drawing a delta for heat or a triangle. Let me just put that in parentheses just to be safe. Yeah, and to be honest, even writing that much, like sometimes people will not bother doing, they'll just show the two reagents and they just react together automatically and form the product. Okay. So, electron withdrawing groups, I guess, let me go back and tweak how I worded things up here just a little bit. Because it turns out you can get it to work if you don't have any electron withdrawing groups on there. So I guess R works best as an electron withdrawing group because you can still get it to go without that on there, just you have to heat it up a lot more. And then at some point you're risking decomposition of your reagents or products. But depending on exactly what's going on, sometimes it'll work okay without any electron withdrawing groups on there. So one really classic example of this is, here's a molecule called cyclopentadiene. I guess if you wanted to be specific, it's 1,3-cyclopentadiene, but it turns out there's no other location the double bonds could be in cyclopentadiene and still have it exist. So okay, so this is cyclopentadiene. It can serve as a diene, obviously, but it can also serve as a dienophile. How did I draw this in the notes? Okay. Okay, so that's how I have it in the notes. So it can work as a diene and as its own dienophile. And you can actually get two copies of this thing sticking onto each other. So again, it looks a little confusing. Let's use dotted lines to connect it. Let's say there and there to connect the ends of my dienophile pi bond with the ends of my diene pi bonds. If you want, you can also number this. That'll help quite a bit too. So let's say 1, 2, 3, 4, 5, and then I'll go 6, 7, 8, 9, 10. And honestly, it doesn't matter how you number it so long as you're consistent. I'm just trying to stick with how I got it in the notes. Okay, so this thing, let's start with our new 6-membered ring and then we can fill in the details. Okay, so that's what we just made. We know we're making a ring of carbons 1, 2, 3, 4 for the diene, and then the 2 carbons involved for the dienophile functional group are 7 and 6 there. Okay, so details we got to fill in. We got 5 sort of poking out into the middle here. And then we have the whole 8, 9, 10 dangling off on the side. Okay, what else? We got pi bonds. The newly formed one is between 2 and 3. And then we also have the 8, 9 pi bond that hasn't changed at all and just kind of stayed the same the whole time. Okay, and again, if you want, you can sort of show this as like a 3-dimensional structure like I drew in the notes, but drawing it flat in plane is also totally fine too, whichever way is easier for you to see. Okay, so interesting fact about this one. You can't actually buy a bottle of straight cyclopentadiene because it's going to react with itself automatically, and so the stuff you actually get in the bottle of cyclopentadiene is actually this dicyclopentadiene, like it's 2 copies of itself stuck together. Okay, so real briefly in the alkenes chapter, we covered polymerization, where you can take a bunch of copies of a molecule and stick them all together into a chain. So poly, which is a lot, and mer, which is part, so many parts. This is just 2 parts, so this is called dimerization. So what this molecule is doing is dimerizing. So it's kind of an equilibrium reaction, like there's going to be most of it in the dimerized form and then some in like the monomer form where it's just 1 copy of the molecule by itself. And so if you actually want to do any reaction with cyclopentadiene, the normal way that you do it in lab is actually put a bunch of this stuff into like a distillation setup, and then you heat it up a bunch. That provides the energy to split off some cyclopentadiene as individual molecules, and then you collect that and you got to react it like usually in an hour or 2 before it all dimerizes and sticks back up together onto itself. So that's actually the reaction that we used to have people do in lab, but it is not a nice smelling chemical, so we sort of got away from that one too. So multiple reasons of, I guess, why we're doing the lab the way that we do it now. Okay, questions about that one? Okay, cool. Alrighty, so requirements for this to work. I guess I sort of telegraphed one of them just on the basis of how I'm drawing the diene. Camera. Okay. So the diene must be able to make this curled up C shape that I'm showing during the reaction. So it has to be able to get a cis, like we covered last time. And in fact, the more time it spends as cis, the easier this reaction is going to be. So if we have something like this, technically that's a conjugated diene, but it's permanently locked S-trans. Like there's no way you can ever rotate that to an S-cis shape. And the same for this guy. There's no way that can ever get S-cis either because you can't rotate around the single bond in the diene because it's locked in a ring. So no Diels-Alder is possible for those 2 molecules, at least not while they're acting as a diene. You might be able to make them do the job of a dienophile, but they're not going to be able to do the diene itself, or be the diene. By contrast, if you have something that's locked always S-cis, say like this guy, or this guy, this, or even this. All of these have two conjugated double bonds that are permanently held in the right position to do Diels-Alder as a diene. So these are going to have an easier time at Diels-Alder than just like the acyclic, like straight up just butadiene thing that I've been showing so far. Okay, questions about those ones? Okay, so if it's locked into one position or the other, it's pretty easy to tell. If it's freely rotating, we still might be able to get some idea of how good this reaction is going to be. If it's freely rotating, then we saw last time that sterics might kind of stop it from going S-cis some of the times, so that might also hamper Diels-Alder. So here's some rotating ones, like linear ones. If we do something like this, where we've got a couple methyls stuck out on the outside and then just H's on the inside, we saw that there is going to be a little bit of bumping, a little bit of sterics between these two H's. But it turns out it's not that big a deal. Like the molecule is still going to pass through like the flat S-cis conformation enough of the time, or get close enough, that it's still going to be okay at Diels-Alder. I guess in the notes I say no steric hindrance in S-cis. We know that's not 100% true, but it's relatively minimal. However, the more and more R group bulk we cram into the middle here, the harder it's going to be to get S-cis, and the worse a diene it's going to be. So if we maybe flip one of these CH3s, let me keep it consistent with over there, and then we keep the rest as H's. Here we've got some sterics in the middle, like this methyl group is bumping into the H there. Probably it's still going to work okay, just you might have to heat it up a bit more to make it go. But if we try to have two separate methyls in the middle, that's going to be a problem. Okay, so if I gave you like 3 different molecules and said, rank how good these are at Diels-Alder when they're acting as a diene, then you could pretty much just estimate, like, once you get them into the cis conformation, how bad are the sterics going to be. Okay, questions about those? Okay, cool. All right, so let's talk stereochemistry for a bit. Okay, so we know that this is a concerted reaction. In the past, when we've seen concerted reactions, I can't think of any exceptions that we've seen to this yet, where whatever stereochem we have to start out with gets conserved throughout the reaction. So things that are on the same face stay on the same face because they straight up don't have time to move around or change stereochemistry at all before the reaction's already done. So that's going to be true here. So the relationships between different groups are conserved. Basically, things that are trans in the dienophile are trans in the product. Okay, and the same for if they're cis in the dienophile, they're going to be cis in the product. So if we're looking at something like this molecule, I've got two carboxylic acids that are cis to each other. Which means that when I do the addition, they better be cis to each other still. So I can show them as either both bold or both dashed, which means in the notes I only show like one option, but really for all of these, you want to mentally add a racemic note to it. I guess for this one it doesn't matter because it turns out to be meso anyway and there's a plane of symmetry, but if I did have, say, like two different electron withdrawing groups, then it would matter whether I showed them both bold or both dashed. Okay, so that's if they're cis. Then they end up cis in the products, and correspondingly, if they start out trans in the dienophile, which is another option, I guess I showed them cis in like the generic version way up there, but you can have them hanging off either way. Then when I stick this thing together, one is going to have to be bold and one is going to have to be dashed. So like that. And again, this one actually is going to be a racemic product because having this one dashed and this one bold is actually a different molecule from the other way around. Okay, questions about that? Yeah.
So it's still possible that they can react even though they're trans?
How do you mean?
To the dienophile, like
Mhm.
how you said before that for the dienophile to be S it's a better reaction?
Right. So the diene itself still has to be S-cis, no matter what, if you want this ring formation to work. But now we're looking at the dienophile, which can be cis or trans. So this part still has to be S-cis if Diels-Alder is going to happen at all. But the actual dienophile can be cis or trans. And both of those will give us two different sort of stereochemical outcomes, if that makes sense. So, yeah. Okay,
So like the other we talked about with stereochemistry,
Mhm.
that was for the diene.
Yeah, for the diene, actually, yeah. So, yeah, so all of these I'm kind of looking at, this is kind of the diene, like in how much time it spends S-cis versus S-trans. So I guess, yeah, that's actually a really good point to bring out for both of you is that even though we use the term S-cis and S-trans, that's sort of looking at the arrangement of the two double bonds in the diene itself. Now we're kind of hopping down here and looking temporarily at the dienophile. So we're looking at, so all of these are like how do the two alkenes in the diene line up. This is looking at how do the two electron withdrawing groups on the dienophile line up. So, yeah. And in a second, we're going to hop back and look at the diene and how any side groups on that line up. So there's like multiple moving parts here, unfortunately. Okay, so any other questions about the dienophile geometry and how that pans out? Okay, cool. So basically, groups on the same side in the dienophile end up on the same side in the product. Okay. Let me actually highlight that. So this is dienophile geometry that we're looking at. For diene geometry, we're going to need a little bit different descriptor because describing groups as cis or trans, we already know the central bond has to be S-cis for this to work. So how we're going to describe it is outside groups end up cis to each other. And then inside groups end up cis to each other. Okay, so let's actually do an example of how that might look. Okay, so we know the diene has to be S-cis, so that's kind of a constant. But what we're going to do now is look at what if we start having different groups on here. So I'm going to say RO for outside, which if you look at it, it's like outside the curve of the diene. And then RI is an inside group. So that's RI here. So I guess I could have sort of brought this in up here where like the more sterics we have on RI, the more sterics we have on the inside groups, the harder it's going to be to do this at all. But depending on what you've got here, like we could just say both RIs are hydrogen or maybe something's going on with deuterium. There's still a bunch of options that we have. So we've got R inside, and then R outside. So if we do this with some dienophile, let's use this one for example, we are going to get a product where both of our R outside groups end up cis to each other. So if I show that RO being bold, this RO is also going to be bold. And then in that case, RI would be dashed in this molecule, and this RI would also be dashed. And I'm going to be vague about the stereochemistry on here for right now, because there's kind of a third thing that we need to cover for that, which we'll do in a second here. But sort of glossing over this part for now, RO is bold, RO is also bold here, and that means that RI and RI are dashed. Okay, so questions about that one? Okay, so I guess the take-home message for this is stereochem within the dienophile is conserved. If it starts cis, it stays cis. Stereochem within the diene is also conserved. If they're both on the outside, then they end up both on the same face. So we've covered relationships just within the dienophile and what it becomes, and within the diene. What we need to cover now is relationships between the groups on what used to be the dienophile and what used to be the diene. So for this setup, how do we know what direction these things are going to be pointing, in other words? Okay. Turns out there's actually two possible outcomes. Depending on conditions, you can actually target one versus the other. And these products are called endo and exo. Okay, so don't know if it's Latin or Greek, but I guess endo means inside in a lot of other words, and exo means outside. So the way to remember it is endo means that the dienophile groups are on the opposite face to the RO groups. So it's, I don't know why they chose to name it this way, but it's basically, sorry, that's our inside groups. So it's basically endo means it's on the opposite face to the R inside. Exo means it's on the opposite face to R outside. Okay, so how this might look if we do this same reaction here, but now we're more thorough about showing stereochemistry. So we got RO, RI, RI, RO, and okay. So we can actually make two different things out of this if we're showing complete stereochemistry. One is make the six-membered ring here. We know that RO and RI here, RO, RI here. And by the way, I'm choosing to show RO as bold in all these examples, but it could just as easily have been the other way around, so long as the ROs always stay on the same face. So mentally you want to have like a little racemic kind of disclaimer next to every single product that I'm showing here in this section. Okay, so we know this part already. But if we show stereochemistry on the dienophile groups, we can show either bold here or the other product we can show is, let's just leave things the same for the diene bits. And then we could show the opposite stereochemistry for the dienophile bits. So like that. Okay. So in, oh sorry.
Like 4 products if you were to write all of the different.
Yes, or possibly less depending on like if some of them turn out to be meso. Like if both ROs were the same as each other and both RIs were the same as each other, then really this is the same as its mirror image. So that's just like only one product there and only one product here. But you would still have minimum of 2 unless you do something involving reaction conditions to heavily favor one over the other, which we'll cover in a second. Good question, thanks. Okay, so in terms of naming these, here the dienophile groups are on the opposite face to our inside. So this is the endo form. Here, the dienophile groups, this carbonyl, are on the opposite face to our outside. So this is exo. Okay. So a whole lot of stereochemistry going on there. I guess it helps to think of it in 3 separate chunks, like what's going on within the dienophile, what's going on within the diene, and then what's going on like in terms of the relationship between them. Because 2 of those things, the first 2 are pretty set in stone and there's nothing you can really do to change them. It's just in the relationship between them that we have multiple different possibilities. Okay, so questions about that one or about any of those? Okay, cool. So in terms of figuring out which one's more favored than the other, endo product is usually going to be the favored reaction for conditions that are more typically used in the lab. You know what, this is kind of confusingly low here. Just going to scoot this up a bit. Okay. There, okay. All right, so endo is usually going to be the favored product. Exo is usually going to be minor. But it can become the major product at higher temperatures. Okay, so I think those of you who took OChem 1 with Professor Jin last semester actually got into kinetic versus thermodynamic products a little ahead of schedule. We're going to be getting a little more heavily into them later in the chapter, but so I'll sort of double back and explain that in those terms in a little bit. But for now, this one is generally assumed to be the major product unless we just heat it a lot, or sort of catalyze it by some other means. So in terms of why that is, come on. Okay. So why endo is favored? It's the ghost of molecular orbital theory rearing its ugly head again. Turns out that if you have a diene, so like this, I'm going to draw it as a 5-membered ring diene just because that's kind of how I have it in the notes. But here's our p orbitals again. And it turns out that if we get the dienophile here, so the diene has its own p orbitals here, and the dienophile also has its own p orbitals. And it turns out that even though they're not officially part of the same molecule, having these two like pi orbital rich kind of flat things like start overlapping and stabilizing each other a little bit actually turns out to make this reaction easier. So this is really hard to show with just my hands. I probably should have brought a model kit, but we're not going to get super far into it. But just in case you're curious, it turns out endo actually provides a stabilizing MO overlap between the two molecules. And when the reaction actually happens, this ends up giving you something where like this bridge here, like R inside, kind of folds out of the way, and it ends up giving you endo geometry. If you're trying to do this on making the exo product, how much time I got? Okay, I got a few minutes. Good. If you're trying to do this with the exo product, then these carbonyls are sort of hanging out to one side out of the way, and so it ends up being less steric crowding in the final product, but you don't get as good stabilization during the actual reaction. Okay, so we'll come back and talk about sterics and I guess kinetics versus thermodynamics once we cover it in a different context. Okay, so one last little bit about endo versus exo that's actually kind of useful to know for the sapling is because we're treating the endo as based on electron withdrawing groups, so if dienophile has one electron withdrawing group and one non-electron withdrawing group, say like a methyl or something, usually endo is described in terms of where the electron withdrawing group ends up. So something like this really what we care about being on the same side as R inside or R outside is this carbonyl, because that's kind of the one that's got the option of doing this orbital overlap and stabilizing or not stabilizing things. So in this case, if we want to show just the endo products, all right, so these methyl groups from the diene are R outside. So we want, if we're making the endo product, this has to be on the same side as our H's, which are R inside, or on the opposite face to the H's, which are R inside. And then we don't really care what the methyl's up to because it's not determining the outcome of this. Okay, and then finally, okay, I'm out of time, but I'll do one more example next lecture and then get into the next topic.